This animation shows how the levels of immunoglobulins change during the specific, adaptive immune response that develops as a result of infection with a pathogen or following immunization. When vaccine antigen enters the body, it triggers an inflammatory reaction. This is initially mediated by the non-specific innate immune system, but subsequently develops to involve the specific adaptive immune system too. Dendritic cells are attracted to the antigen. The antigens are taken up by the dendritic cells, also known as antigen-presenting cells, and presented on the cell surface membrane. They migrate to the lymph nodes. The primary specific adaptive immune response is now underway. T cells that recognize the specific antigen being presented by the dendritic cell bind to the antigen. This process activates the T cell to become a helper T cell. Meanwhile, immature B cells pick up the antigen on their surface immunoglobulins and process it. Once processed, the antigen is presented on the surface of the B cell. There are approximately 10 million different types of immature B cells. Each cell carries a unique immunoglobulin on its surface that can bind to only one specific antigen. The helper T cell binds to the antigen on the B cell and then releases cytokines that stimulate the B cell. Once stimulated, B cells undergo rapid proliferation and differentiation into plasma cells and memory B cells. One such B cell can produce thousands of daughter cells in a few days. This action increases the capacity to produce stronger binding, soluble antibodies. The antibody concentration rises in the blood serum. Further stimulation of B cells by T cell action leads to affinity maturation, where high-affinity antibodies are produced. The concentration of antibodies is now at a peak. Infection is over. The plasma cells die off and the antibody concentration falls. This is known as the contraction phase. The specific adaptive immune system retains memory of the antigen for future use. Memory B cells remain in bone marrow and may circulate between lymph nodes, ready to recognize the antigen again if it presents itself. They continue to secrete a low level of high-affinity antibodies. This is known as immunological memory. When the body is exposed to the same antigen again, These high-affinity antibodies in the blood bind to the antigen. This acts as a signal to circulating cells that recognize the antigen quickly, and the secondary response begins. Memory B cells and T cells are activated more rapidly than on primary contact with the antigen, as the antigen is already familiar to the immune system. The memory B cells proliferate and differentiate into plasma cells that produce high-affinity antibodies in higher concentration than found in the primary response. Often, during the secondary response, further maturation occurs, leading to the antibodies that are more specific. Consequently, each time the body is exposed to a particular pathogen, the antibody response becomes quicker, more sustained, and of higher affinity, offering even better immunological protection.